Good afternoon, I'm Spot On Weather meteorologist Matthew Euler, and today we're going to move into the next training video, and I'm going to be covering atmospheric circulation. Here's a nice image of the Earth looking down from space, and there's a lot of different swirly cloud patterns associated with this weather satellite image. There's a lot of motion going on through winds. A lot of things are happening. So let's get right into the training today. And we're going to start off with an overview. And first and foremost, from last week's training, I mentioned how the sun plays into setting things in motion in the atmosphere. This heating, the incoming solar radiation, really kicks things off and moves air both horizontally and vertically and mixes things up. Now, air rises and expands when it's warmed. And air sinks and contracts when it's cooled. Horizontal motion, what we feel as the wind here on the Earth's surface, that's caused by differences in the atmospheric pressure. And air is going to move from higher toward lower pressure, as I mentioned in the previous training video. Now there's differences in temperature, and those differences in temperature is the main cause of pressure changes on the Earth's surface. This unequal absorption of the sun's radiation by the Earth's surface due to varying land surfaces results in circulation of air. And what do I mean by that? Different surfaces are going to heat up differently. For example, on a hot summer day, when you're walking over a sidewalk or a roadway, you're going to feel much hotter over that surface during a summer day, as the incoming solar radiation tends to heat that surface more efficiently. Whereas if you were to move off the sidewalk over a grassy area, the temperature above that grass would not be as warm because there's unequal heating, for example, between a sidewalk or a roadway and grass. Now, overall, due to the relative position of Earth with respect to the sun, much more radiation is absorbed near the equator than at other areas, with the least radiation being absorbed at or near the poles. So the principal factor affecting the atmosphere is incoming solar radiation and its distribution across the latitudes on Earth, as well as the differences in the incoming solar radiation from one season to the next. Now this graphic in the bottom right, I wanted you to really think about things here in the training today. Notice the size of these circular areas on the globe at the lower right. And this is all based on different latitudes. So if we were to look at the size of the circle, that's the area that the sun is actually covering. It's the surface area the heat is reaching on the Earth's surface. That surface area, the circle, is going to be much smaller over the lower latitudes, closer to the equator. But if you look at the top and bottom of the globe, you'll notice how that circle is much larger. What that means is the incoming solar radiation is spread out over a much larger area in the polar areas, as compared to the more direct heating in the smaller circle and the tropical areas. And you can do this experiment yourself at home by getting a blank sheet of paper, getting a pencil, and a flashlight, and shine the flashlight directly down. Hold the flashlight right above the piece of paper, and then shine the flashlight directly down. Hold it straight above the paper. Draw the circle when you hold the flashlight in that manner. And then you can tilt the flashlight to maybe a 45-degree angle to where it's not directly over that blank sheet of paper. Tilt it to more of a 45-degree angle, and then draw out the size of the circle that light is basically created on the paper. And you will see a major difference between more intense, the smaller circle from the flashlight would represent lower latitude or tropical area incoming solar radiation, more direct heating per unit area. And then as you tilt the flashlight, that larger circle would be synonymous to the incoming solar radiation at the polar areas. Now the general circulation, since Earth heats unequally, and when I mean unequally, I'm going to refer to across the latitudes. So since Earth heats unequally due to the more direct solar radiation hitting towards closer to the equator and the tropics, and the less direct radiation, the larger circle over the polar areas, the heat is going to be carried away from the hot area in the tropics to the cooler areas known as the poles. This global movement of air, which acts to restore heat balance on Earth, is known as a general circulation. The bottom right-hand graphic on this slide shows the atmospheric absorption of solar energy at various latitudes on the Earth. And you'll notice the darker shaded orange colors there are generally associated with areas closer to the equator. If we look at northern South America, if we look at parts of Africa, if we look at parts of Southeast Asia, all those areas have the brighter orange shading, which indicates the solar radiation is much more intense in those areas. Now, if you look at the higher latitudes, you notice the blue shading on that graphic in the bottom right, and that is less solar radiation, less absorption of solar radiation in the polar areas. So there's a big difference in heating across the latitudes, across the Earth in general. Much more heating and absorption occurs at the equator, less heating at the poles. Now, the world temperature gradient overall. What do I mean by when I say the word temperature gradient? Temperature gradient is the rate of change of temperature with distance in any given direction at any point. Now, the world temperature gradient, this refers to the change in temperature that exists in the atmosphere as we go from the lower latitudes at the equator to the higher latitudes at the poles. Now, the temperature differential, the difference between temperatures across the latitudes, that causes a general atmospheric circulation or wind, which can be compared to the temperature differences in a heated pan of water over a gas burner. Look at the pan there in the upper right-hand graphic there. This is the pan that has water in it that is being heated over a gas burner. Now, as that water is heated, it expands and its density is lowered. This reduction in density then will cause warmer, less dense water to rise to the top of the pan. And as it rises, it's going to cool and is forced to the edges of the pan. So you get a circulation where the center of the pan, where it's the hottest, the water, as it's heated, the density again is lowered and it rises towards the top of the water surface. And some of that water is actually being evaporated. And that's why you see the steam, the water vapor over the pot, the boiling pot of water. Now, the circulation then goes as the air rises in the middle of the pan. It then moves towards the edge of the pan and sinks again and cools. So it sets up a circulation similar to the atmosphere. Here it's going to cool further and sink to the bottom, that water on the edge of the pan, and eventually work its way back to the center of the pan where it started. So you've got a nice circulation going on with the atmosphere. Now, one other thing to mention is the atmosphere is a fluid. Air within the troposphere, which is our layer of the atmosphere closest here to the Earth's surface, that may be compared to the water in the pan that I just showed in the previous slide. Most direct rays of the sun are going to hit Earth near the equator, and that causes a net gain of heat there. And air at the equator then is going to heat and rise and flow in the upper atmosphere toward both poles. Upon reaching the poles, that air is going to cool, it's going to sink back toward Earth, where it tends to flow along the surface of the Earth back to the equator. Here's a simple Earth circulation model. Now, this does not take into account the rotation of the Earth. And in fact, I'll show you a slide here a little bit later that's going to show a similar diagram of what the circulation of the atmosphere would be on a non-rotating Earth. Of course, we know this is not reality, right? But just to show you, if we didn't have any rotation of the Earth, the equatorial region would have the area of greatest heating, and then the polar areas would be the areas of least heating, whether we talk about the North Pole or the South Pole. And you'll notice the black arrows in the diagram would show air heating and rising over the equator, moving to the upper portions of the atmosphere, flowing in the upper atmosphere right back to the polar areas where the air would get colder and sink again and flow at the surface back towards the equatorial regions. Again, we know this is not realistic because the Earth rotates, resulting in an apparent force known as the Coriolis force, which I mentioned in the previous training video. And that's going to deflect the air to the right of its intended path in the northern hemisphere and to the left of its intended path of motion in the southern hemisphere. So this rotation then results in a constant change to the area that's being heated. Now, Earth is covered by irregular land, such as mountainous terrain, and water surfaces. We see plenty of that on the Earth's surface, whether we're talking about the oceans or whether we're talking about rivers or lakes. Now, the land and water heats much differently. Land heats and cools 5 times more efficiently than the nearby water surface, and that actually results in what's known as a land sea breeze circulation in the summer when the heating is the most intense. Now, the worldwide temperature considerations, we have to take into account other things when we talk about how temperature is distributed across the world. Now, regions under the most direct rays of the sun, those areas are going to absorb more heat per unit time than those areas receiving the oblique rays. And that kind of gets back to what I was showing in this slide, right here in the bottom right, and how you see the more direct, smaller circular area, heating per unit area over the tropical locations close to the equator as compared to the polar areas. The bottom right-hand graphic, note again the bigger circle. So the light of the sun, the radiation is going to pass through a much larger area of the atmosphere, and it's much more diffuse and spread out. And so that's what that gets at. Now, other factors when we talk about worldwide temperatures are length of daylight hours. And these are going to vary based on the latitude where you're located on Earth. So near the equator, there are always about 12 hours of daylight throughout the year. But the sun's rays strike this area more directly. The equatorial areas do not have pronounced seasonal temperature variations because of this. So they have similar daylight throughout the year, around 12 hours of daylight, 12 hours of darkness. And the sun really doesn't change its position in the sky very much throughout the year at the equator. If you look at the bottom right-hand graphic, I'm showing both the amount of daylight hours on various parts of the Earth's surface. One is for the summer solstice around June 21st, the first day of summer in the northern hemisphere. The other is for the winter solstice on December 21st, around that time period. And that is when it's the northern hemisphere winter, the first day of winter in the northern hemisphere. So you'll notice, depending on the latitude of the Earth, where you're located, for example, we already talked about the equator at 0 degrees latitude, generally having 12 hours of daylight and 12 hours of darkness. It doesn't matter if we're talking about summer solstice in June or the winter solstice in December. Now, if you notice at the summer solstice, how as you move north in latitude, as the northern hemisphere, the North Pole, is tilted toward the sun in the summertime, on June 21st, you'll notice that the farther north you go in latitude in the northern hemisphere, the greater the amount of daylight hours. So, for example, at 23.5 degrees north of the Tropic of Cancer on or around June 21st for the summer solstice, there is approximately 13.5 hours of daylight. If you continue to move further northward towards 66.5 degrees north latitude at the Arctic Circle, there is 24 hours of daylight at 66.5 north all the way to 90 degrees north. 6 months of daylight. All right, and then the southern hemisphere is the opposite effect. Now, in the winter solstice, you'll notice as you go poleward towards farther north latitudes in the northern hemisphere, the amount of daylight decreases and decreases until it reaches a point to where you have 24 hours of darkness around December 21st from the 66.5 degrees north latitude, the Arctic Circle, to 90 degrees north latitude, the actual North Pole. So, just wanted to really emphasize how the amount of daylight hours plays into worldwide temperature considerations. This is based on latitude. Plays a big role in how long the sun will be out for a particular location to heat the actual air mass. So during the summer in the northern hemisphere, all areas north of the equator are going to have greater than 12 hours of daylight. During the winter, the situation is reversed, where latitudes north of the equator have less than 12 hours of daylight. Now, there's a large seasonal variation in the length of the daylight hours and the seasonal differences in the angle at which the sun's rays reach Earth's surface, causing seasonal temperature differences in the middle and the high latitudes. And when I say middle latitudes, I'm talking about between 30 degrees and 60 degrees north or south latitude. The high latitudes are going to be from 60 north to 90 north. So that's the general latitude belts I'm talking. Now the weak temperature gradient in the subtropical areas, which is about 30 degrees north and south, and the steeper gradient poleward is going to occur. You're going to have steeper temperature gradients basically occurring poleward in the winter season of each hemisphere, and I'm going to show you that right now. So the image on the left, that's showing the temperature distribution for January. The image on the right is showing the temperature distribution for July. And you notice these solid dark lines. These are known as isotherms, or lines of equal temperature. So if you were to go and any one particular, just pick one of these black dark lines, solid lines, everywhere on that line is whatever the temperature is labeled as. Now, January, if you look at the northern hemisphere, especially the United States, Europe, take a look at how closely packed these lines of equal temperature, or isotherms, are in January. So in the winter hemisphere, which January, we're in winter here in the northern hemisphere, in the United States, Canada, right? Notice how much tighter that gradient is, the temperature. And I've seen this in the United States alone, where you might have a temperature in early January of like 85 degrees in Miami, Florida, and it may be negative 20 degrees Fahrenheit up in northern Minnesota. It can be that large of a temperature gradient in the winter season. Whereas the graphic on the right shows July, which we're coming up upon, and notice how much further apart the spacing is of those isotherms, lines of equal temperature, the solid black lines. So now, let's say I go pick the same locations for July. I may have a temperature of 88, 89 degrees down in Miami, Florida. And then if I go up to northern Minnesota, my temperature may be 85, 86, maybe only a 3 degree Fahrenheit difference. So the temperature gradient is much tighter or steep in the winter season as you go poleward or further north in latitude. Now the global pressure distribution, if we talk about temperature changes are going to result in pressure changes. And so this unequal heating of Earth's surface due to the tilt of the Earth on its axis at 23.5 degrees, its rotation throughout a daily rotation, 24 hours in a day, and the differential incoming solar radiation is going to result in the wide distribution of pressure over Earth's surface. Now, generally you have low pressure area which lies along what's known as intertropical convergence zones in the equatorial region, and this ITCZ is the area at which the trade winds converge or meet. The southeastern trades from the southern hemisphere actually meet and collide with the northeasterly trade winds of the northern hemisphere. And generally along this ITCZ, this belt of thunderstorms, you generally get some type of tropical disturbances. Our tropical cyclones and hurricanes are actually born from this cluster known as the ITCZ, this line of convergence. Now at the polar areas, we generally have permanent high pressure areas which remain near the surface because of the very cold temperatures there throughout the entire year. Now remember that cold air is much denser and heavier. So therefore you get a lot more higher pressure in areas that are cold throughout the year. And meanwhile, we have what's known as piling up of air in the subtropical high pressure areas at 30 degrees north and south latitudes, and that also produces a belt of high pressure on the globe. Here's a look at the global pressure distribution. Again, I'm comparing January on the left versus July on the right. Big differences here. For example, in July, I tend to have more pronounced low pressure systems or low pressure belts located around 60 degrees north latitude in January. And I also tend to get stronger, colder high pressure systems over land masses in northern latitudes in January. Now, if I go to the right-hand graphic and show you July, things are different. You generally have the weakening of the low pressure systems. The low pressure belt weakens at 60 degrees north latitude in July. And you generally have stronger, larger, high pressure systems that exist at the 30 degree north and south latitude area. Something that's known as the Bermuda high pressure system over the Atlantic Ocean, which influences our weather significantly across the eastern United States in the summertime by pumping in a lot of heat and humidity. Whereas the sprawling high over the eastern Pacific, we call it the East Pac High, that is also ridging further northward, having a stronger influence poleward in July as compared to January. And you just notice the absence, there's less cyclonic storms, there's less low pressure systems over land in July as compared to January, where we've got a lot more dynamics, the jet stream is much stronger in January. So circulation again on a non-rotating Earth, this is referred basically to thermal circulation because it's caused by just differences in heating across the globe. Air is heated and rises again over the equator. That creates areas of low pressure, while the air is cooled and sinks over the polar areas, high pressure. So if you take a look at this globe again, just showing you, the yellow areas near the equator would be the hot zones where the air is rising. As it rises, it's eventually going to reach upper troposphere and then spread out and work its way in the upper atmosphere towards the poles, then sink, and the air would flow back from the poles to the equator, right? You see the purple arrows there showing the flow in both the northern and southern hemisphere. But we know this doesn't exist because the rotation again of Earth, and that's going to affect that thermal circulation. That rotation is going to result in that deflection to the right of movement of air in the northern hemisphere and the wind, and to the left of movement in the southern hemisphere. Again, that's that Coriolis force, that apparent force. And you look at the graphic at the bottom right, you notice how the winds tend to bend. They don't just blow straight from north to south, right? They tend to bend. And again, that's due to the Coriolis force. And this results in pressure zones or low pressure zones along the equator, a high pressure zone at 30 degrees north and 30 degrees south latitude, another low pressure zone at 60 degrees north and south latitude known as the polar front, and then high pressure zone again at 90 degrees north and south at the polar areas. All right, so when we talk about the whole global circulation, and we have to reference this, it's something known as the three-cell theory. Now, Earth is generally divided into 6 circulation belts. There's 3 in the northern hemisphere, there's 3 in the southern hemisphere. The dividing lines are generally the equator at 0 degrees latitude, 30 degrees north and south latitude, subtropical high pressure area, and 60 degrees north and south latitude, where we get a lot of storminess. And these 3 cells are known as the tropical cell, the mid-latitude cell, and the polar cell. So when I talk about tropical cell, I'm talking about that area on Earth that lies between the equator and 30 degrees latitude. And what we have is a process known as convection, which is a vertical transport of excessive heating at the Earth's surface into the upper atmosphere. And that convection at the equator and thunderstorm development is going to cause the air to heat and rise. And when that air reaches the upper troposphere, again, as I mentioned, it tends to flow toward the North Pole and then also towards the South Pole. So by the time the air has reached 30 degrees north latitude, the Coriolis effect has now deflected that wind so much that it's actually moving eastward instead of northward. And this is going to result in piling up of air, upper level convergence at 30 degrees north latitude, and a descending current of air. Whenever the air sinks in the atmosphere, we call this subsidence toward the surface, which forms a belt of high pressure. So if you were to go out on the water in a ship, in a boat, and you were going to be generally moving at somewhere in the vicinity of 30 degrees north latitude, you would typically find very nice weather. Now, when the air reaches the surface at this particular belt, part of it flows poleward to become part of the mid-latitude cell, and the other part flows toward the equator, where it is deflected again by Coriolis force, forming the northeast trade winds. Now, the trade winds are some of the most persistent winds known on Earth. I actually lived in Hawaii for a few years, and pretty much throughout the whole entire year, the wind direction is from the northeast, due to this global three-cell theory. Moving north now to latitudes 30 to 60 degrees north latitude, that's where we live here in the United States. The air, this is known as the Ferrel cell, by the way, or the mid-latitude cell. The air which comprises the cell will circulate poleward at the surface and then moves southward or equatorward aloft with rising air currents at 60 degrees latitude, and that's known as the polar front. The polar front is the area where your polar easterlies are going to meet up with your mid-latitude westerlies, and it's going to create a lot of rising air motion. And then you also have the descending currents, which occur at 30 degrees latitude high pressure belt. So the winds, both at the surface and aloft, are going to blow from the west in the mid latitudes. And as an example, weather generally tends to follow the direction of the wind in the mid latitudes and moving from west to east, because our jet stream tends to blow from west to east in this particular mid latitude Ferrel cell. And then finally, the polar cell. This lies between 60 degrees north latitude and the North Pole. The circulation within this cell begins with the flow of air at a high altitude toward the pole. This flow then cools and descends at the North Pole, forming a high pressure area in the polar region at about 90 degrees north. And after reaching the surface, this air usually flows equatorward or southward and is deflected by the Coriolis force, so that moves from the northeast. So this is what causes those polar easterlies. This air then converges with the polar flow from the mid-latitude cell, and that is then deflected. Air rises upward with a portion circulating poleward again and the remainder back to the equator, towards the equator. This results in a semi-permanent low-pressure area at 60 degrees north latitude. We typically find these the strongest in the wintertime, especially in the vicinity of the Gulf of Alaska as well as Iceland. I've heard some really crazy stories about Iceland. People that have actually lived there, literally they have to tie down the dumpsters with heavy-duty lines in the wintertime in Iceland because the wind can be so strong. And this is due to that persistent low-pressure area and the stronger pressure gradient, the stronger gusty winds associated with these stronger lows in the wintertime. So world winds in general, just kind of to summarize today's training. In vicinity of the equator is a belt of light and variable winds. This is known as the doldrums. I've actually been on a boat before down around the equator, and the air is very still in the doldrums. There's just not much wind at all. And if you were to have a sailing vessel or relying on wind to push you along, it would not be a good time for you because there's just really no wind to really push you along in that boat. So I've been there and observed this personally. You got all these towering cumulus clouds, but you really don't have much in the way of wind. Now on the poleward side of those doldrums, as we go north, are what's known as the trade winds, which again is the predominant wind system of the tropics. These easterly winds are the most consistent on Earth, especially out over the oceans. I've been on plenty of trips out over the water, especially on the Pacific side, to where these east-northeasterly winds, they continue all the time. There's just no let up, and they're really very rare to get a change in wind direction in this particular belt. Near 30 degrees north and south latitudes lie the subtropical high-pressure belts. The winds are light and variable once again in that location. These areas are referred to as the horse latitudes. The winds became so light in the past that sailors and mariners would have to, if they were hauling horses, to lighten the load, they would throw their horses overboard because there was no winds to push their sails along. So that's why we come up with the name horse latitudes. They throw the horses overboard to try to lighten the load to allow them to move along a little bit more quickly. And Christopher Columbus, he sailed in this latitude belt, before he actually discovered America and actually into the Caribbean area as well. So it's a real fascinating wind belt. One other thing I wanted to mention about 30 degrees north and south latitudes, this is where the world deserts reside. So for example, the Saharan Desert, this is where it's just you get some of the largest deserts occur around 30 degrees north and south latitude because of the fair weather you typically get there, sinking air motion and dry air masses. Now the prevailing westerlies, these are located northward of the northeast trade wind belt. So the prevailing westerlies are located on the poleward side of this tropical high pressure belt and are persistent across the U.S. And then further north or poleward of the prevailing westerlies near 60 degrees north and south latitudes lies the belt of low pressure known as the polar front zone. Converging winds result in rising air currents and poor weather at this zone. Here's a look at the world winds graphically. I'm just kind of tying everything together. Again, you'll notice you have the doldrum belt that's generally located in the center of the diagram. That's generally where the winds are light and variable, as I mentioned. And by the way, the weather there, the doldrum belt is very, very humid. very humid. Within the northeast trades and the southeast trades, these are one of the more persistent wind belts, the trade wind belt for the Earth. You generally have subtropical high pressure belts at 30 degrees north and south latitude, and the wind's going to flow at the surface from that high pressure towards a lower pressure at the equator where that intertropical convergence zone resides. And that's why you get more of a northeast wind with the deflection of the Coriolis effect. And then you look at the westerly wind belt, 30 to 60 degrees latitude. Again, that's where we live in the United States. And then the polar easterlies between 60 and 90 degrees north latitude. Again, where the general predominant wind is from the east to northeast in the polar areas. So there's a lot of exciting things to look at. When you look at the worldwide weather, you want to look to see where your location is located at what and within what circulation cell, the cells we went over. Is it in the tropical cell, the feral or mid-latitude cell, or the polar cell? And that is going to help explain a lot of the weather that is experienced at that particular location. So a lot of interesting things. I remember learning this for the first time when I went through the meteorology school, and I just remember drawing out these different belts, and it took me a little bit, but then I really caught on to the concept. Think about a rotating Earth. You look above the North Pole, the Earth is rotating in a counterclockwise manner, and then the Coriolis effect turning the winds to the right of their intended path of motion in the northern hemisphere and to the left in the southern hemisphere. And it really, really all makes sense. All right, that wraps the training up today. We talked about atmospheric circulation. I certainly hope you have learned something today. Thank you for subscribing to the Spot on Weather YouTube channel. It's greatly appreciated. Feel free to send me an email. You can always send us an email. We're also located in Facebook as well as in Twitter. We're most active in Facebook and Twitter with our daily forecast updates, as well as searching the Spot on Weather Weebly website. And you can see all of our latest forecasts as well as a lot of other fun things. All right, take care, everybody. I hope you enjoyed the training. Spot on Weather. If we're not spot on, we're not doing it right. Have a great evening, everyone.